And it'll become available like at 12:02 in the morning, so, and it goes to bed at like 12 at night, so it'll be available for 24 hours. Do it on your own, but use your book, use whatever resources you need, but do it on your own. Okay, so it's on a time release thing, it's already built, you're good to go. It'll be about the first homework, not the second one that you'll do tonight. So no, there'll be no elongation, no strain. We'll do that today in class, and then you'll do a homework set on it. We'll move forward. You did 2, 3, and 5. How was it? Piece of cake, right? Any questions on 2, 3, and 5?
Maybe just check the answer.
I don't know what the answers are. What'd you get?
For number 2, I got
Okay, wait, let me read it. 6-inch diameter concrete test cylinder is loaded with a compressive force of 113.1 kips. What's a kip?
1,000.
1,000 pounds. So we're talking 113,000 pounds. Concrete cylinder. Determine the stress in the cylinder. 6-inch diameter. What'd you get?
tips.
4 square inch per square inch.
For KSI?
Yes.
Okay, and did anyone look up concrete? It didn't say look it up, right? The book is really bad.
There are different type of concrete. and
Yeah,
that's
there
not
is.
specified.
There is,
There are
but
5 in total.
But check it out, in the back. There is SI units, don't mistake that, and then there is average properties of some common materials. And here they are, and there is concrete, and as Jorge said, there's 2 of them, and there's actually more than 2.
There's
but
5 in total.
There's 2 very common ones. And notice you won't get all the properties of
What
concrete.
table is that?
This is on page 501. Average properties of some common materials. Okay? So now, like we talked a little bit about this tensile yield strength, right? That's when a material yields. Guess what? Concrete doesn't do a lot of yielding. It's like titanium. It's not going to stretch a whole lot. It's not going to compress very much. It's just going to blow up when it decides to fail. Okay, very dramatic. So we don't even have a yield strength for concrete, but we do have a ultimate strength.
The blood.
That? No, it's highlighter. I don't think I'm bleeding yet today, but I bleed daily because that's just what I do. Because I work with my hands, because working with your hands is good for your brain, just so you know.
I said no idea.
It can be on your truck, it can be on your car, it can be in your garden. I build, right? I'm building a golf platform for my dad. What?
Is there any proof to that, or is that just a say?
No, there's actually research that's proven. So you know who wrote the research? This is fascinating. Mechanical engineering PhD person went out, worked 5 years in research, but was a motorcycle enthusiast and finally gave up the PhD research to work with his hands and have a Harley Davidson shop. And so he did research on how many people have migrated from like a high tech to a low hands-on type of job and what their like rating on happiness is. And he literally proved through some research, you know, with statistics, which is always flaky, that you can be much happier if you find, I think it's more you find something you're super passionate about, but working with your hands is definitely beneficial.
I work about 15 years as a aviation technician
Mm-hmm.
and 20 plus on and off as a machinist. And I still have my
Yeah,
8 fingers.
nice,
and my 2 thumbs.
yeah. I haven't taken off a finger yet. All right, so anyway, back on task
It's
here.
because I'm
No.
a machinist, they cut themselves.
That's not blood, not blood, it's highlighter. But see, ultimate strength, standard concrete, 3 KSI. How much you come up with? 4 KSI. So right at the limit of high strength concrete. But it'll hold it, that's a lot of weight on a concrete cylinder like, I think it was 6-inch, right?
Yes.
That is a lot of weight. Concrete's amazingly strong. All right, anyone else get 4 KSI? Yeah, okay, check. What other one? 3?
32 ounces.
Yeah, so there's two segments to it, right? So does the load change? No, the load transfers through the object, right? So we know stress is P over A. So if one of those is changing, then your stress is changing. And in this case, the area is changing. The stress is going to be higher or lower in a smaller area. Smaller.
Much higher.
Gotta be higher, yeah, because area is in the denominator, and as that number gets smaller, the whole number gets bigger, right? So, yeah, stress should be higher here in segment. What's this one called? BC. What'd you get in BC?
31.18 KSI.
Anybody else? Yeah? And then what about in AB?
18.75 KSI.
Yeah, and did they give us the material? Looks terrible. They didn't. Yeah, so if they don't give us material, then we can't check it. So then we're just like calculating a stress for some academic purpose, and I despise that, so. I wish they would give us materials on everything, because then we could like say, oh, that's a good stressor. Oh, oops, that's not gonna work. Kind
On
of
the
thing.
next one, they give us a steel bar.
That's-
What type of steel?
That's gonna be mild steel, but that's a great comment. So number 5, the following member, right? Number 5? Following members are in subject to actual axial tensile loads. Axial load, what's that mean? Yeah, this, right? In line with the long axis. So we will do bi-axis stress, which means 2 axis. One will be axial, like that, and the other one would be like cross-section, right? Or bi-axis. All right. Yeah, steel bar 25 by 50, and then a wood post, and then a steel tie rope.
Wait, that's
you-
4.
Oh, that's 4. Darn, I like that one. I should do 4 next time. All right. Steel bar 2 by 2. What was that one? 4,000?
Yep.
Anyone remember the yield of mild steel? No, 36,000.
36.
So mild steel is called A36. And that stands for 36,000 yield. So if you're getting 4,000, we're like 9 times under the limit. That's good. What about the W4 by 13? How'd you get the area? Look it up.
Through the
But
table.
Yeah, go to the table, look it up.
Nick said a different answer. It was close though.
Okay,
4,000.
perfect. And W shapes are steel, typically mild steel, but they can be different steels. So if we don't know, like on a quiz, I'm going to tell you the material, so you'll be able to compare it right away. But if the book doesn't actually tell you like a specific kind of steel, then we just assume A36.
Okay, but question on the table itself, on the soft material,
On what?
on the soft steel. It also 836, but it said or A501, that's
Right.
what that means,
What's that mean?
yeah,
So that 501 is another type of mild steel.
okay.
It has just a different carbon content, but it has the same material properties. So it might have different corrosion resistance. It might have a little different surface finish, that kind of thing. But the properties, same. Yep. And I think they give you high strength, yeah. And they give you stainless, yeah, they give you stainless. They give you 1040, that's hot rolled. So those are the common steels that get used out there. And of course, there is a lot more. You can get any kind of steel you want, so. Excellent. So good. You guys are pro already. One day and they're pro, Ben. It's crazy. You're pro too.
I have no idea what's.
I know, but you will. All right, turn them in. Pass them to the left, I guess, if you want, unless you need to get up and go. I thought you were wearing horse riding. Yeah.
One day. You wanna think of?
That's what I thought too.
Unfortunately, not. for
Practice or game today?
Practice.
When's the next game?
Saturday.
Lost.
We did play in Centralia. And then we played
Where
Not
was
the
that?
Grace
Grid,
Harbor.
but this is
We
the-
played at class.
Go to Grace Harbor?
Yeah.
Was it raining like?
That's all.
Yeah, it wasn't like rain, it was more like a mist.
Yeah, coastal. Is there anything else? That's a great move.
It's, this is not.
I was struggling so bad, it's like.
I'm.
Well, I felt like it was. It's like you took less.
I mean,
You
you
I never
can say
really done it.
excuses
Right.
to COVID.
But
Just
yeah,
like-
I just- I did about 1,000 left.
Yeah.
I was like, you know what, I'm just gonna,
Did I tell you I went to the Beavers game
oh no,
Tuesday night?
Uh-uh. Oh, wait, yeah, you did,
They hit the
You
ball.
just don't know. You just-
really?
It's only.
Yeah.
I mean,
It's just easier.
Three
to
elements.
A standard grounder is just.
I don't know, I didn't know.
Real.
Okay.
Poor
Based on-
Gonzaga, they didn't even what.
Oh, really?
14-0.
I just started it,
then.
then.
17.
Leave me the hell alone.
And
No
of course,
pressure,
it's like by-
no pressure, keeps pressure.
Yeah.
But, I mean, it's kind of, it's good for Gonzaga, it's not good for the Beavers, but.
Sure.
They made some stupid mistakes, you know, how you play stupid against.
Yeah,
Yeah.
I played worse against
You
it.
do, you play worse. All right, let's push forward. Wow, chapter 15, that's really pushing forward. Let's go back to chapter 9. All right, just a quick review. Our stress equation, P over A. Right? This is all kinds of tensile stresses, also called normal stresses or axial stresses. Right? And then shear. We haven't done any work in shear yet, but you're gonna have a homework set in shear. Oh, I should show you that because it's a little deceiving maybe or confusing. Let me look at it. Where does it say? Yeah, here's where it's, so you're gonna do 10 as a homework set, and it says in the bolted connection of figure 9.12. Figure 9.12 is in the chapter. You gotta go looking for it. So it's not anywhere here. Okay, so whenever they refer to a figure, that's like, oh, here's a figure, 921. Right, so we're looking for figure 9.12. Figure 914. Figure 912 right here. So when the homework problem says, go look at figure 912, that's figure 912. Is yours different?
But yeah,
What's yours say?
is it? Mine's right here,
And that's figure 912?
9.12 up here, example,
No,
wait.
no,
what?
no, no.
Oh, I
You
got
gotta
it,
find the one that says figure.
Oh,
I think
right.
that's on the
I got
next, yeah, go back a page. Yeah, that's why I'm showing you, because
Welcome
it's
back.
really weird. So when the book problem refers to a figure, you gotta go looking for it. Yeah, you're gonna need a picture of that, Ben. Sorry. Exactly. So you're gonna do shear stress on this one, and they actually show you what we talked about last time. You have to think about what has to fail, and you have to use that area. So if it's a multiple bolted connection, every bolt's gotta fail. Like if it's a 10 bolt connection, all 10 bolts have to fail for this thing to be failed. So when you do your stress P over A, you're gonna include all the areas in shear. So this one, the plate, the bottom plate would go one way, the top plate would go the other, and it would have to take those two out. So you use the areas of those two bolts for your shear calculation. Okay. Good, questions? I think you have a punch problem too. So the problem with a punch problem is you have to, again, think about the area that's gonna fail. Right? So when you take a round punch and you send it through a material, you're trying to punch a hole, right? What has to fail? It's this outer ring that has to fail when you drive something through a piece of material. Right? So it's the circumference and it's the thickness of the material that has to fail. It's like a ring that you would put on a finger. It's that area. That makes sense? Shear's a little different because you have to think about, oh, what area would fail, right? And in this case, with this punching down through this, it's this outer ring that would fail. So you have to calculate that. Circumference is 2 pi r times the thickness gives you the area. All right. Good. Yes, it's this 11 one. And you're actually going to compute the force. So we did that last time too. Right? If we have stress equal to P over A, and they give us like a material property, they say, hey, this is steel, and it'll actually fail at 40,000 PSI, right? Then we know this. So the problem says the material, we can look up the failure stress, or they give us the failure strips. And then they say, and it's, the punch is this big, so then we know the area. What we don't know is P, if they ask for the load. So you can solve this equation 3 different ways for 3 different things. That's when this class gets complicated, because they're gonna just throw a lot of stuff at you. And then say, how, you know, how much load can this carry? And you have to go, oh, loads in this equation, right? Do I know the material? If I know the material, then I know the limit, I can look it up. And do I know the area that's gonna fail? Then I can calculate the limit that would do it, right? So we don't just use it to calculate stress, we use it to calculate load, and we also use it to calculate area. And it seems like a super simple formula, but it does get confusing. You have to know what you're giving, kind of have to understand what that is. If they say, oh, this material will fail at 40,000 PSI, that's a stress. 40,000 PSI. That's the property of the material. So that goes here. Then we could calculate load if we knew the area. All right. Yeah.
In some cases, when they give you the material, they will give you the area also, right?
Yeah. Yeah, so that would be what we call an analysis problem. In other words, hey, here's the system. Is it good or not? Is it okay? Is this gonna work, right? So if you're given the material and you're given the area, maybe asked about the load, then you're just analyzing the situation, right? It's not like you're trying to design. Design would be, we don't know the area. How big of a thing do we need to put in there? Then area becomes the unknown. We're gonna have to know the load, and we're gonna have to know what material. So you have to know 2 of the 3 to solve for things. So yeah, gets tricky when we get into design, but we're not there. We're just still gonna hack out some stress. All right, that's the homework set. This one you did. We're gonna do modulus elasticity today. We're gonna do strain, and that's probably gonna be enough, especially if we practice it a little bit. So this we've got defined. We haven't had a lot of practice with it, but that's the stress, right? So we know stress is equal to P over A. All right, so I have to take you on a little bit of a journey to understand this modulus elasticity thing. I think they do it a little bit in the wrong order, because this is now, what I'm going to talk about is kind of chapter 10 stuff, but you have to have that concept to understand modulus elasticity. But this is a graph, and this is the stress strain graph. So stress, we know, is equal to load over area. We've done a couple stress calculations. So when we take something, and I'm just going to draw our standard block thing, a square rod, and we pull on it. And I don't know the size, maybe it's 1 by 1 steel, right? So it's pretty strong. We kind of played with that last time. So the way the stress strain graph gets developed is just like this. You take a test piece of a material, you load it in a tensilometer, and it pulls on it. Okay, and it starts with 1 pound. Right? And when you pull on anything at 1 pound, it changes its length. That's what strain is a change in length. So as we increase the load, and since this is P over A, and A doesn't change, it's 1 by 1. So really the only thing changing here is the load. As the load increases, the strain increases. Right? So at 1 pound, it stretches a little. At 2 pounds, it stretches that exact same amount some more. That makes sense? At 3 pounds, that same amount again. At 4 pounds, that same amount again. It's a linear curve, a straight line in the beginning. We're not putting much load on there. When we get to 5,000 pounds, then maybe, it's stretching a lot more, but it's still linear. So this region of this straight line where we increase load and we increase the stretch is called the elastic region. If you let go of the load, it goes back to its shape. Remember, with steel, it's really small and very hard to see, but it's happening. Rubber band would be like very easy to see. Stretch it, 3 pounds, let go of it, goes back to rubber band. That's the elastic region. Rubber band, you go far enough, it breaks. You've obviously gone past the elastic region. All right. Okay, we'll turn that on. All right. So we want to stay in this region. And in this region, stress and strain, remember this is strain, this is stress, they're equivalent to each other. There's a relationship between them. That relationship is called the modulus of elasticity. And we refer to it as E. I think that's a epsilon. That's a Greek lowercase e, epsilon. So the modulus elasticity, there's a relationship between stress and strain and the modulus elasticity. This is a material property. In other words, E is going to be different for steel. It's going to be different for aluminum. It's going to be different for titanium, different for wood. We can look it up. So if we know the material, we know E, right? We can look it up. It's a material property. Kind of like tensile stress for a material or yield stress for a material. You can look it up. It's different for all the different materials. It's in this table of common materials, right? And E is also here. Modulus of elasticity. For steel, the modulus elasticity is what? For mild steel. Mild steel's here. Here's modulus elasticity. It's how much? 30,000 what? KSI. Got to really sink this in because that's 30 million PSI. Okay, yeah, it is, Ben.
Sorry.
30,000 KSI. K stands for 1,000.
Oh.
So it's really 30 million PSI. Modulus elasticity is a big darn number. Yield strength, we've talked about that, is 36 KSI, 36,000 for that same material. So the stress is much different than the modulus elasticity.
Basically the same ratio as kips versus how many pounds, 1,000 pounds, right?
Yeah, kips is 1,000. Yep, exactly. So you just add 3 zeros to that number to get PSI. Sometimes you'll need PSI, sometimes you won't. You can use KSI. So if your load comes to you in kips, then you can just use KSI because you have kips in the system. If your load comes to you in pounds and then you're using modulus elasticity and it's in KSI, then you need to get it to PSI, pounds per square. And that's 30 million. All right. So what the modulus elasticity is this relationship between load and stretch. That's what you need to wrap your head around, like everything that gets loaded will deform. And if we want to know how much it deforms, which we do, as engineers, we want to know, like, how much is this going to deform? We don't want it to deform into, we don't want the cylinder ring to expand and weld to the cylinder wall. We don't want that to happen, right? So we need to know the elasticity of the ring material. We need to know temperature. Temperature is a big thing in pistons, and we're not doing temperature yet, but we will do temperature in here, right? We're just doing load. So maybe the cam or the piston rod is being loaded by the explosion of the fuel, right? And that piston rod cannot deform too much. If it does, we're gonna have all kinds of problems. Okay, so we calculate this stuff all the time as far as deflection goes. And E is what does it for us, because it's the relationship between this load and strain. Well, strain is defined as delta over L. That's a Greek, I think, lowercase d. And that is the change. The change in length. So when we pull on this, I'm gonna pull on it with 4,000 pounds. And it's 1 by 1, and we'll make it A36, which is just mild steel. Okay, so when we pull on it with 4,000 pounds, it changes length. That happens. And if we want to figure that out, then we have to use this equation and this equation and the modulus elasticity to figure it out. Okay. Anytime you're doing, this is deflection, this is how much it changes. L is the original length. So we would need to know that this thing is 30 inches long. So, original length. All right. So, strain, stress, modulus elasticity. Anytime you're going to calculate a deflection or how much something changes, we can only calculate that in this region. If we're outside of the elastic region, it's not predictable. We can't calculate it. I mean, we can calculate it, but our number's not valid. So that means we need to know, like, here's the whole curve. We need to know here, this is the stress yield. We need to know that our stress is in this elastic region before we try to calculate a deflection. If it's outside the elastic region, we can't calculate it. It's not valid. Okay. So first thing to do when you're trying to calculate a deflection or how much something changes is you got to calculate the stress. And we've done that. What's the equation for stress? P over A. You can answer that for any time I say stress. P over A. Any kind of stress. So step one, when you're trying to figure out how much something stretches, is calculate the stress and make sure you're within the elastic region. This is A36. If it's under 36,000 PSI, we're good. So how do we calculate stress? P over A. How much is our load? 4,000. And what's our area? 1 times 1, 1 inch squared, right? Oh, I put it here. How much is my stress? 4,000 PSI. It's divided by 1 squared, keeping the numbers simple, right? So our stress is 4,000 PSI. The yield is 36,000. Are we within the elastic region? Yield is 36,000. Yeah, we're way down here at 4,000. So this is like our calculated tensile stress of 4,000 PSI. So on the graph, this mild steel graph, we're way down in the straight line region. Agreed? So that's this yield stress is where the end of the straight line is. And this is the elastic region, and this is the region we want to work in. But we need to check to see that we're in that region. When we're given numbers, that's the first thing we want to do, is check that. Once you learn that you are within the elastic region, then you can calculate a deflection. Okay, 4,000 pounds, it's going to stretch some. We have to figure out how much. The equation E equals stress over strain. What does stress equal? What's the equation for stress? P over A. And then what's the equation for strain? Delta over L. This is like a term-long fundamental equation that we will just try to work on. The problem with this equation is there's 1, 2, 3, 4, 5 variables. And that means you could solve this equation for 5 different things. That's where it gets complicated.
What's the delta over L?
Delta over L is strain. Strain is here. Stress over strain. Stress over strain.
Oh, okay.
Delta over L. So I'm just breaking the formula and breaking this formula down into the components. Stress equals P over A and strain equals delta over L. The book does this and it's to develop the formula. But if you understand that concept of E equals stress over strain and then stress equals P over A, strain equals delta over L, then you can generate this equation anytime you need it, in any form you need it, right? Yeah.
What is?
Delta is the amount of change. So it's hard to draw. I'll exaggerate it. When we pull on this actually is going to move to here, right? This surface is going to move to here. That right there is delta. Does that make sense? It's the amount of change. And it's what we want to know typically. Like if someone says, okay, here's all the loading, how much does it deflect or how much does it change in size? It's like, oh, delta. That's what we want to know.
We measured that in American Standard.
You can measure it. Well, you can't always measure it. Sometimes you just calculate it. Like we're just going to calculate it. But it'll come up in inches. Depending on the unit you're working with, right? So if everything's in inches, you're going to get inches. If it's a metric problem, then you're going to get millimeters. All right. So that means this is what we want to solve for. Our delta. Right? If we want to know how much it stretches. So then you just kind of go through it and you go, okay, do I know everything else? Do I know the load on our problem here? 4,000. Do I know the area? 1 inch squared. Do I know the original length?
30.
30. Do I know E? I told you the material, so we can look it up. I know all the pieces. I just have to be able to do algebra.
30,000
Yep, 30,000 what?
KSI.
KSI or 30 million PSI. Yep. So depending on what your unit is, we have pounds here. So that means we're probably going to need pounds in the E. Unless you change it to 4 kips, then you could use your 30,000 kips, right? So, yeah. The equation solves out. We have to solve for this, so we can write it out in kind of in position. This is, I'm going to use 30 million pounds per inch squared. That's E. We just looked it up for mild steel, right? Equal to 4,000 pounds divided by 1 inch squared. That's my area because it was 1 by 1 over delta, what I want to know, and the original length of 30 inches. I Everyone know how to do the algebra to that? Not so bad, right? The good news is it's so common that they give you the formula for delta. Right? It's so common that we calculate this. It's really PL over AE. But that's just what we developed right here. Right? This is the same thing. You just have to be able to do the algebra to get rid of this. All right, what do we get for? So the simplified version is delta equals PL over AE. So this turns into this when you solve for delta. So it's load times, because this flips up, this goes down, and then E comes over, delta goes over. So that's your algebra. They do it for you. But yeah, we need a number. Calculate a number for me. It's mild steel. We're putting 4,000 pounds on it. But it probably doesn't stretch a whole lot. I would guess it's a pretty small number. Anybody got a number? Huh? 0.004? Anyone else get that? Somebody confirm my number. Yeah, so what are the units? If I think about this equation, the units are pounds times inches over area, inches squared, and E pounds per inch squared is how I did the unit analysis for this equation, right? So this flips up, we have inches to the third on top, inches squared below. So we're left with inches above and nothing below because the pounds cross out. Which makes sense because delta should be the change in size, right? It's the inch change.
1,000.
Yeah, 4,000ths of an inch is how much it changes. 4,000 pounds on a 1 inch by 1 inch, did this last time, that's my 1 inch by 1 inch. Right, and I hang two Honda CRVs from it. My Honda CRV is about 2,000 pounds. And it deflects that much, it's crazy. That's why we love it. Doesn't deflect much. Now, you raise the temperature 20 degrees and then that gets a lot longer. So that's like 10 times longer than that. So when we do thermal expansion, you'll be like, what? It expands that much? But yeah, it does. So we'll add all this stuff together towards the end of the term. All right, that was a lot. Like this is a very fundamental equation. We use it for a lot of stuff. So just think about the number of different ways we can run this equation. Like if we're given the deflection, and then we're given the area and the material, we could calculate a load if we knew how long it was, right? How much load would it take? So 5 different ways you can run that equation. 5 different word problems. It's like, this gets really crazy. But what you have to think about is, what do I know? What am I trying to find out? The hard part is, for students is like, if the problem starts with a wood beam, they just told you a whole bunch of information by saying this thing is wood. Because you can look up properties for wood, right? You can look up the yield stress, the bending stress, the modulus elasticity, a lot of things. So as soon as it says the material is this, you know a lot. I mean,
There's different types of wood.
Yeah, they would have to say.
There's plywood, there's like.
yeah, but they would have to say the type of wood, not just wood. You are correct. We talked about that on Tuesday. And we don't have a lot of wood properties in here. And I think you do have to be careful when you go online to look up properties, just make sure you're getting a good source. But these are the woods that we have in the back then. Doug fir, southern pine, hem fir, eastern white pine, and redwood.
But I've never heard of them.
Yeah, exactly. So in our area, we're Douglas fir fans. We have a lot of Douglas fir lumber. And we are hemp fir fans. We have a lot of hemlock fir combination. When you graft hemlock and fir together, it grows twice as fast as a Doug fir. That's why we like hemp fir. We can make a lot of lumber fast compared to a Doug fir. Its properties are different, right? Because you combine the two. They're actually a little bit better than Doug fir. Doug fir is 900 in bending, hemp fir is 1,000. And then in tensile 625, and a little worse, a little not as good as Doug fir in tensile. All right, good, good, good. Let's practice this a little bit. What do you think? I think. How much time do we have? We have enough. All right, so we're gonna take this cable. And it's a 1/4 inch diameter aluminum cable that is 40 inches long. Okay, so 40 inch, 1/4 inch is like your little finger diameter. Right, I have fat fingers, so it's a little less than my little finger. But it's here, this is 1/4 inch. Now that's the diameter of 1/4 inch.
Not bigger.
Oh, for the folks watching the video, there you go, 1/4 inch. I have a ruler, anyway. 40 inches long, right? And we're gonna hang 2,000 pennies. And we'd like to know how much it stretches. £2,000 on a 1/4 inch aluminum. What do we need to check first? Before we think about how much it stretches, what do we have to verify? You yield, that we're within the yield, that we're under the yield, that it actually hasn't broke. Maybe it breaks, right? And then we can't calculate deflection. So what's the yield of aluminum? It's a material property. 35 what? KSI?
35,000.
Anybody else want to verify?
35 KSI.
All right, so yield 35,000 PSI or 35 KSI, same thing, right? That's for aluminum. All right, so how much calculated stress do we have on this thing? That's what we have to check. We have to check that we're under this. Yep, we gotta go stress equals P over A. What's our load? 2,000 pounds. What's our area? It's dying. Ready? Area of a area of could do pi r squared, which is 0.125 squared, an 1/8 inch squared, or you could do pi d over 4.
60.
1/4 inch diameter.
Yeah, so
Half of a 1/4 is, no, so the radius is half of the diameter. Yeah,
49,000.
it should be an 8, which is 0.125.
I got 49,000.
Anybody else get a number? For stress? Jorge, what do you get, Jorge?
Oh, I haven't, no. I
Oh,
got the-
careful.
Sorry, the area of the. I didn't do the whole thing.
Don't forget pi.
2000, sorry.
Big,
It could be big.
40,743.
40,743.
0.6, 0.7.
0.7 PSI, right? Pounds per inch squared. And then what does aluminum think of that?
Not good.
Not good, stop the problem.
That's
It
what I
is not within the elastic range. This thing actually just shredded itself. So even though the question says, how much did it stretch? The answer is, it broke. It didn't stretch. Okay? That's why we check the stress right away. The book doesn't do this to you. It's a happy world with the book. A good world, right? But I do this to you on quizzes and exams. Because this is reality, like you gotta check stresses first before you can calculate any kind of deflection. All right, so we need to make a change, so we actually can calculate a stretch. Let's make it twice as thick. Let's make it a 1/2 inch in diameter. Now what's the stress?
20.
Yeah, it's really the same equation, right? 2,000 divided by pi 0.25 squared. How much?
10,185.
PSI? Yeah.
Yes, I.
And what does aluminum think of that? No problem. Yeah, well under the 35,000, right? All right, so that means for this diameter, we can actually calculate a stress. And we can calculate a deflection, how much it stretches. Because we are within the elastic region. It's predictable. So that means I can run this equation, PL, our new equation, over AE. What's our load?
Oh,
2,000. What's our length? Original? 40 inches. What's our E value? Ooh, we gotta look that one up for aluminum, right?
10,000 KSI.
And then the area we can put in there. 2,000 pounds, 40 inches. E is, how much, Jorge?
E, you said?
Yeah, how much is E?
E is 10,000 KSI.
Aluminum, 10,000 KSI. I'm gonna put in 10,000, 10 million pounds per inch squared. And then what's our area? It's that area right there, yeah. So that's PLAAE. Are we expecting a big number or a small number? Definitely a small number. How come I get 0.041? Did I do something wrong? 0.041? Yeah. 0.041 inches. 41 thousandths is how much it stretches. Okay? So when you're calculating these deltas, they're usually very small. But if you have a system where the clearances are 10,000s and you're looking at a stretch at 40,000s, you have a clearance problem. So we have to know how much these things deflect, especially in tight mechanical systems. And then we're gonna throw temperature into the mix at some point, and that's really gonna muck things up. So you gotta be able to calculate your load deflections and then your thermal deflections and add all that up to say, yep, it'll work, or nope. Once this thing warms up, it's gonna all hit each other. We can't have that, so. And this is just kind of the beginning steps of calculating a change. When something stretches, how does that happen? Like, where does the material go if it stretches? Yeah, so the 1 by 1 is no longer 1 by 1. If you stretch it, the 1 by 1 now is something a little smaller than 1 by 1, which actually drives the stress up because your area just got smaller. So we would have to go back and calculate the stress again with this new reduced area to figure that out. That's down the road when we do biaxial deformation, when we figure out how much something shrinks in cross section. Right, based on its stretch. Oh, I think we're good. You are ready for your homework. Break it into its pieces. When you read the problem, write out what you're learning as you read the problem. As soon as it says mild steel, boom, I know, E. Go look up E and write it down, because now you know E, right? As soon as it says a yield stress or a ultimate stress, write it down, because it's giving you information. Yeah,
We're still using grid paper, right?
green paper,
Yeah, grid paper.
that's preferred, but there's some that are resistant to it. They're rebellious. I'm not gonna mention names or look at people.
Yeah, some line.
I prefer green paper, but I'm not that much of a, yeah, not that hard.
And most of this stuff covers the material from the first home, right? So it's sort of like.
Yeah,
Okay.
yeah,
That's fine.
you'll be fine.
All right.
Good job.